Hi students, now we are going to derive the relationship between torque and angular momentum. Before that, I will recall what is Newton's second law of motion. According to Newton's second law of motion, the force acting on a body is equal to the rate of change of linear momentum. So dp by dt, where p is the linear momentum. So what is the term which is analogous to force, which is acting in rotational motion? The effect produced by force in linear motion is analogous to the effect produced by torque in rotational motion. So I can replace the term F by torque tau. So this must be equal to d by dt of rate of change of, here linear momentum P must be replaced by angular momentum, that is dl by dt. So what is the relationship we have to derive now? We have to derive the relationship between torque tau and the angular momentum L. So we want to prove that the torque is also equal to the rate of change of angular momentum. That is the derivation we have to do. So first of all, I have understood which relationship we are going to derive is tau is equal to dl by dt. So for that, let us start from the expression for torque. So the torque acting on the body, is given by tau is equal to I into alpha. Is it not? So if you start this expression, F is equal to dp by dt, finally what you will arrive at, F is equal to mass into linear acceleration. Is it not? This is what we have derived in the Newton's second law of motion. Similarly, if you continue this and you can prove that torque tau is equal to I into alpha. So analogous terms, force is replaced by torque, mass is replaced by moment of inertia. So finally, linear acceleration must be replaced by angular acceleration. So this is the beginning equation for this relationship derivation. I start with the torque acting on the body, tau is equal to I into alpha. Okay. Now, this is the first equation. Alpha is called as what? Angular acceleration. Angular acceleration, and which is given by rate of change of angular velocity. So d omega divided by dt. So this is equation 2. Okay. So in general, acceleration is defined as what? Rate of change of velocity, be it linear motion or angular motion. So in rotational or angular motion, angular acceleration alpha is equal to rate of change of angular velocity. Omega is the angular velocity. So I am going to substitute for alpha in the first equation. Therefore, what is tau now equal to I into d omega by dt. Okay. This moment of inertia I is a constant. So even if I take inside also, the value will be same. So I can write tau is now equal to d by dt of I into omega. Now I is the moment of inertia and omega is what? Angular velocity. Both are contrasting. When the moment of inertia is very large, opposition will be very large and omega, speed of rotation, will become very less. But the product will be always a constant. Is it not? So what is that constant? I omega. I omega is also equal to what? This is moment of inertia, this is angular velocity. So this I into omega product only we have earlier derived and that is equal to what? Angular momentum. Understand? So I into omega is equal to what? Angular momentum. This is similar to what? Mass into linear velocity is equal to linear momentum. Similar equation, whenever you write them, you will get a clear idea of comparison of translatory motion and rotational motion. So d by dt of I into omega. I into omega product is equal to what? L. Therefore, tau is now equal to d by dt of L or dl by dt. So in vector form, tau vector is equal to d by dt, rate of change of angular momentum vector. This is the relationship between torque and angular momentum. I hope you must have understood well. Fine.